Okay, so when you are using a sensor or a actuator, there's data flowing from the sensor to the microcontroller, actuator to the microcontroller and back. And that data has to be then interpreted by the processor on the microcontroller. Now, we've seen that there are analog signals, there are digital signals. These microcontrollers and computers, for that matter, can only understand zeros and ones. And so how do you take something which is analog, say 0 to 5 volts, and convert that to zeros and ones so that the computer can process it is basically what we are going to learn about in this chapter. So it's actually pretty simple, but then it'll all make sense as I go through some of the things about data acquisition. There are two things we'll be talking about here. One is data sampling. The second is data quantization. Okay, so what I mean by that, by data acquisition, which I just mentioned, is that there is some voltage which is coming to inside the device. And we are trying to understand how a computer or microcontroller can acquire, save, use this analog voltage Okay, so what we'll do is I'll break it down. I'll first talk about data sampling, which is very important, and then I'll talk about data quantization. So we'll cover these two parts separately. Let's talk about data sampling. Okay, so what I mean by data sampling is that when a computer or a microcontroller has to interpret this data, which the signal. Okay, so what's happening is there is a voltage and time, and I've shown this because I have access to the complete signal, which I saved, and then I plotted it. But how will a computer do that? Well, it will have to sample the signal. So on the x-axis is time, and by sampling, I need to set a frequency at which this signal, at which the computer can pull the particular pin on it so that it can take the information. So let's say that it samples here, then here. And this is usually equidistant, right? So let's say those are the samples it takes. And so what happens is, let me draw this. This is the original signal, but when you reconstruct the signal from the sample data points, we'll essentially draw straight lines, right? Color. Okay, so here you can see that it looks like the purple is almost on the red. So this seems like this sampling, the way I've sampled it, is pretty good because it can reproduce the signal to a fair extent. The straight lines are a good approximations to the red line, right? And that's because the curve is sort of like smooth and the sampling rate is fast enough. Okay. But then the question is, what is the sampling frequency we need to choose for a random signal, right? That's important, because if you don't sample the right frequency, then you will not be able to reproduce the data. So there is something called just put here. This is the sampling points. And then to summarize what I said, that is the actual data. And this, which is the interpreted data. So this is the actual signal. And this is the reproduced signal. They both line up, look similar. So the sampling frequency is good. Okay, now I just sort of ballpark put some sampling points based on what I thought was good way of extracting the data, and it worked. But if you're given a general signal, how can you determine what is the right sampling frequency? So what is a good sampling frequency? Okay. So the answer to this comes from a famous mathematician called Shannon. I forget his first name. He was from, I believe he's from MIT. He came up with this thing called Shannon sampling theorem. His first name actually is Cloud Shannon. Okay, so instead of giving you the definition of what sampling theorem is, I'm just going to tell you what Shannon sampling theorem tells you. It tells you that if Fs is the sampling frequency, which is something you need to determine, which is unknown, and Fmax is the maximum frequency in the signal. Okay, so a frequency is more evident in something which is periodic. Like if I say it is sine t, then you know that the frequency in radians per second is 1. If it's sine 2t, it's 2, and so on. But for something which is less obvious, like say, what is the frequency of e raised to omega t, or x square plus x plus 2, and so on. There is a way to do that. There is something called a Fourier series, which I think I wrote down some time back. Fourier series sort of takes the input signal and breaks it down into frequency components, and that's how you can figure out what the frequency component of a signal is, and that's what you'll use in this particular theorem. So now we have computed Fmax from, let's say, Fourier series. If it's not obvious what the frequency is, then Shannon's sampling theorem says that to reproduce to capture the frequency content of a signal, Fs, that is the sampling rate, which is an unknown, you need to figure that out, should be at least equal to twice the maximum frequency. Okay. Note that this is only to capture the frequency content. Okay, this is what you need. Okay, so now I'm going to illustrate why this is true by showing you an example. But this frequency, 2f max, is also known as the Nyquist frequency. Okay. So next I'm going to illustrate how sampling at twice the natural frequency, twice the maximum frequency gives you the frequency content of a signal by showing you an example. Okay, so here, this example illustrates Shannon sampling theorem. Okay, the best way to do this is to cook up a signal which has a known frequency content, and then we'll just try to sample it at different frequencies and see what the resulting waveform would look like. So here we go. So here we have a sinusoid. So let's say that, move it down. So we'll choose the sinusoid with a certain frequency. So let's choose. So let's choose B equals sine 2 pi t. Okay. Here, if you know this is similar to sine omega t. Right. So the frequency is 2 pi. But then what we'll do is we'll try to write the frequency in terms of time period. So we know that the time period is 2 pi divided by omega. And so this will be 2 pi divided by 2 pi. So the time period is 1 second, which means that the frequency is 1 over time, which is 1 hertz. Right? Okay, so this signal has a frequency or a time period of 1 and a frequency of 1 hertz. Okay, what that means is if you make a plot of the sinusoid sine 2 pi t, what you'll see is that at t equals 1, so at t equals 0, clearly this is a 0. At t equals 1, we'll have sine 2 pi, which will be 0, and then sine 4 pi, it will be 0, and so on. So we can write 1 here, 2 here, 0, and then we need to join this 0 here, but we know that it takes a peak. Well, at sine t equals half also, it will be a 0, right? Sine of pi is 0. So it'll be a 0 here, 0 here. So it will look something like this. Okay, so this is, let's say, the voltage. Okay, now, since this signal has a frequency of 1 hertz or t equals 1, let's see what is the effect of sampling it at different frequencies. So let's sample at fs equals 1 hertz. Okay, and so when I say 1 hertz, you can choose when you want to start sampling. Let's say that we choose to sample, let's say here. This is a measurement. And then we need to wait for 1 whole second because 1 over fs is the time, is 1 second. So if you wait for 1 second, you sample here and so on, right? So if you now take this particular sample points and plot them, okay, so what we've done here is we have to plot this point. This is the same as this one. And then this one is here. And then join them by a straight line. okay, we'll essentially see that it is flat. Okay, so something which is a sinusoid, when we reconstruct it at its own frequency, we see it's flat. It says it's a constant, which is clearly not true. So let's now try to see if we can ramp this up. Let's take sampling at 2 hertz. Sorry, 2 hertz. So Fs equals 2 hertz, which by the way would be t equals 0.5, because half of 1 over t is the sampling frequency. So let's say that we sampled it here. Okay, now we need to go with sample again at 0.5 seconds. So that would be, this is approximately 0.5, so it's slightly over there. So it's here. Then again, 0.5 seconds would be here. So we have this point, this point, this point, and this point. Let's just see what we get on the reconstruction. So we can, the first dot here, the second dot here, third dot here, fourth dot here. And now we need to connect that by straight lines. Okay. Now let's do this at a slightly higher frequency, say 4 hertz, which means that Ts, which is 1 over Fs, is going to be 0.25, which means we'll get 4 samples for the first second, 4 samples for the next, and so on. So let's just assume that we get a sample here, 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 1, 2, 3, 4, 1, 1, 2, 3, 4. So you can see that there are 4 samples. In this second, 0 to 1, we have 4 samples. And then we have 4 samples in the next second. So let's draw that here. First point is here, second point is here, third is here, fourth is here. Let's join it by straight line. Okay, so what we see is the following. When we sample it at 1 hertz, then the reproduction, this says there's no frequency content. That the reconstruction is saying that this signal is a constant, there's no frequency in it. When we sample at twice the frequency of the signal, which is, by the way, the Nyquist frequency, we see that the time period is actually 1 second. This is 1 second. So this works. It says that the frequency of the signal is 1 hertz, or the time is 1. Okay, so this is faithfully reproducing the frequency of the signal when we do with the Nyquist frequency. What happens if we go 4 times the Nyquist, 4 times the maximum frequency? We have, again, we'll have the same thing, which is between this peak and this peak, we have 1 second. So this also predicts hertz equals 1 second. Okay, and maybe this, so in a way, this example illustrates that the Nyquist frequency is very important because it is able to reproduce the sample, the natural frequency of the signal. Now, Though this works with the frequency content, it doesn't quite reproduce the amplitude. So what I mean by that is the actual amplitude of this signal is right. So the actual amplitude is right here. But this the reproduction on the right sort of underestimates it, right? So similarly here, if you see this is the natural frequency. So amplitude is wrong. Okay. And this phenomenon is known as anti-aliasing. That is, it cannot reproduce the actual amplitude of the signal. Okay. Now, if you want to reproduce the amplitude as well as the frequency, you probably want to sample much higher at a much higher rate, right? Not twice, but maybe 10 times or something like that. So you'll see that when you are using a device, you will normally have want to sample it as fast as possible. So typically people sample at 1 kilohertz, which is 1000 hertz, 1000 times per second. So here we are talking about 2 times per second or 4 times per second, but 1000 hertz, which is normally what people do, is 1000 data points per second. You could also, for some things, you could also go lower, like 200 hertz or 200 times per second. It just depends on the dynamics of the system. If the system is changing rapidly, then you probably want a very high frequency. If it is changing slowly, you want a slower frequency. So for example, if you deal with something of the order of days, like say the weather, that's like changing every few hours versus something which is happening in your circuit, which is probably changing every few milliseconds. You'd use a different sampling frequency to cycle it. So how do you figure out what is the frequency to sample in a signal which looks like this? So here's an example. So let's say that the output V is something like this: 5 cosine pi t cosine 4 pi t cosine 8 pi t cosine 16 pi t. Compute the Nyquist frequency. Okay, remember that Nyquist frequency is the minimum frequency at which you need to sample the system so you can reproduce the frequency component of the signal. So what you do in this case is your main bottleneck in something like this is the value which is the highest frequency, which is changing much faster. So the frequency which is changing fastest is this one, 16 pi t. Okay, so 16 pi t is the fastest frequency. So we will base our calculation on this one. On this frequency. Okay, so here's how you do it. So we know that the way you represent cosine sine is something like cosine 2 pi ft, and this is similar to cosine 16 pi t. So here 2 pi f is same as 16 pi, and so the frequency, in this case it's the max frequency, is 8 hertz. So we have Nyquist frequency is the twice of that. That's the answer. Okay.